Today we're going to be talking about some applications of differential equations. And this is actually a newer video and a newer, I don't want to say topic, but I'm more highlighting this in the past few years because my students, when they come back from the AP test, they didn't understand when they did actually have an application of a differential equation. So that's why I'm doing this. Okay, so rate of change of y is directly proportional to x. So this is an algebra 2 skill. Okay? The rate of change of y, dy dt, is directly proportional to y. Oh, I read it as x. Is directly proportional to y. And directly proportional have a constant of variation, I think it's called. Okay, so now let's solve this differential equation. Separate out our variables. So I have dy over y is equal to k dt. I take the antiderivative of both sides, and I make sure that I take the antiderivative correctly. kt plus c. And just because these are going to be talking, I know the types of functions we're going to be dealing with. These are going to be growth. We'll see. I was going to say something, but I'm not going to do it now. I'm going to wait. So I have the absolute value of y is equal to c e to the kt. Now, hopefully you realize what type of function that is. That's our growth and decay function. So that's what I was going to say a minute ago, is I was just going to say I could take away those absolute value signs to get me that formula. So you need to understand, you need to be able to go between those two functions. You can jump right to it if you want. Okay? You don't have to show the antiderivative. So, exponential growth and decay. So if y is a differentiable function and y prime equals ky, then, so this is my differential equation and this is my solution curve. Okay, c is the initial value, that's key. K, proportionality constant. I think I called it constant variation. And then if you're growing, k is greater than 0. If you're decaying, you're less than 0. So, the rate of change of y is directly proportional to y. So said dy dt is equal to ky. Remember, that gets me right to y equals c e to the kt. Okay, and then when t equals 0, y equals 3. That's your initial value. Let me show you why it's the initial value. This thing goes to 1, so c equals 3. So they give me this, 3 e to the kt. So I use this idea to solve for k. So I plug in y equals 12 when t equals 1. Okay, so now I go through and solve this. And quite honestly, this is just pre-calculus or algebra 2 right now. Okay, ln of 4. I would leave it as ln of 4 because we want the most exact answer as we possibly can. Okay, so now I have 3e to the k, oh, I just found k. 3e to the ln of 4 times by t, okay? And then at this point, I just have to plug in t equals 5. And I'm going to do that in my calculator because I have a whole number sitting here, and I kind of find it kind of interesting that that is a whole number without decimals hanging out. Ln of 4 times by 5. Oh, it does work out. So we get that. Okay, so an experimental insect population increases according to the law of exponential growth. So remember, our law of exponential growth is this. And there were 250 insects after the 3rd day of the experiment and 400 insects after the 4th day. So what they are giving me here, so they are giving me the 3rd day, I have 250. I have 400 after the 4th day. Approximately how many insects were in the original population. So what I need to do is I need to solve for C, essentially. So they give me 2 points. So what I'm doing is I'm just plugging in my points into that general equation I have, and then solving for C. So that I have a system that I can solve. So now I plug in and solve. I have them both equal to C, so I have 400 over e to the 4k is equal to 250 e to the 3k. God, and how did I solve this? I guess I cross-multiplied. So I cross-multiply 400 e to the 3k is equal to 250 e to the 4k. And then if I take and I divide 400 over 250 is equal to e to the 4k over e to the 3k. Well, I have here 400 divided by 250, that is 8/5 equals e to the k. So the ln of 8/5 equals e. I don't know why I put equals. Oh, Marnell, get it together. You're focused on something else right now. So k equals ln of 8/5. And you don't need those absolute value signs. Let me erase those. Okay, so I have that now. Now what I have to do is I have to now plug that back in to my original equation. Y equals c e to the ln of 8/5 times t. I want to know when that initial, I want to know how many approximate were in the original population. So we have to reapply one of our original initial conditions. So I plug in, if I plug in correctly, That was, I lost my T. So I'm going to plug in that. So I have, don't want you guys to get confused. 250 equals CE to the ln of 8/5 times by 3. And then solving that for C, you get 61 insects. Okay, moving right along. This is a really good question because it's a really good application in my opinion. Okay, so I have here the rate of change of the number of foxes, N of t in a population. I wonder, foxes, isn't that foxen? Anyway, in a population is directly proportional to 550 minus N of t, where t is time in years. When t equals 0, the population is 250. When t equals 3, the population has increased to 300. Find the population when t equals 5. Okay, so the rate of change of the number of foxes. So the rate of change of the number of foxes is directly proportional to 550 minus N of t. And I'm just going to write it as big N, just to save myself a little bit of space in here. Okay, so now I do dn is 550 minus n, which equals kt. I'm sorry, it just equals k. I don't know what my problem is today. dt. Separate out my variables. Take your antiderivative if you need to show the u substitution for this. Make sure you do that. Okay, I'm going to multiply by a -1. E to the negative kt plus c is equal to 550 minus n. And I am going to kind of basically flip the location of everything. So I am going to say n equals 550 minus e to the kt plus c. But remember that c, that e to the c can come down and become a c here. I'm going to make sure I do it right. Okay, so when t equals 0, my population is 250. So c ends up equaling 300. So now I have a new function. Okay, now I need to plug in t equals 3 increase to 500 to solve for k. And I want to make sure that I set n equal to 500. Okay, and solving this, I'm not going to go through solving this. 1, because it's pre-calculus. 2, if you need that, please come in and see me. But 3, I'm running out of space. Okay, so then now I know my n of t formula is 550 minus 300 e to the negative 0.59. Ooh, but it's positive because I have a negative. I think this actually is a negative because it's growing. Your population is growing. So, oh, I have negative in my notes. So that's my formula. And then to find use red. Let's use a different color. And a 5, you just plug in 5. And I just want to see if I get the same thing. I don't, because I'm trying to type. So when I plug in 5, I just paused the video and did it in my calculator. I get 534. And I should have on here round to the nearest fox, so 535. Another really good application of differential equations is Newton's law of cooling. And I kind of adjusted this a little bit to what I had previous to this. Okay, so the rate of change of temperature of an object is directly proportional to the difference between the object's temperature and the temperature of the surrounding medium. Okay, so Y is the object's temperature. This is our surrounding medium. And we have this differential equation. Do I expect you to memorize that? No. Do I think this is really fun and cool? Yes. Why do I think that? Because I take a frozen pizza out. I cook a frozen pizza in the oven. I take it out of the oven. I need to know when I can eat it. Okay. So, making a stew. You take the stew off the stove. The temperature of the stew is 180. So that's telling me at time 0, my stew is 180. The room temperature is 74. Okay, so that's my surrounding medium. That's why I have 74 written there. After 5 minutes, the stew is cooled to 155 degrees Fahrenheit. Differential equation for the cooling of that is that. The reason it gave us this is because typically on the AP exam, that's what they'll do, is they'll give you what the differential equation is. And then I want to find an equation for the temperature Y of the stew at any time T. Okay, so let's see if we can do this. So we want to separate out our variables. Okay, I have an initial condition. When I plug in that initial condition that's up here, I don't need those absolute value bars, so I really have here my Y is 180 minus 74 is equal to K times 0 plus C. So C ends up being the ln of 106. So now I have this equation. I don't need those absolute value bars. So e to the kt plus ln of 106 is equal to y minus 74. Okay, I'm going to add that 74 over. Remember, ln, e to the ln of something is just 106 e to the kt plus 74. Okay, so again, what I did there is I separated that out into e to the ln of 106, which equals 106. Okay, now I need to find, after 5 minutes, I've cooled to 155, so that gives me another point. That gives me the point 5 minutes, 155. That's going to help me find my K. 155 is equal to 106 e to the kt plus 74. All right, so I subtract 74. Then I divide by 106. But I forgot to plug in that t was 5. It's because I'm rushing and I'm trying to I'm actually focused on something very different right now. So the ln of this number so I'm going to solve this. And again, what I use is like the previous answer, I should say, in my calculator. So I get k to be negative 0.05379. Hey, that's what I got. 7, 8. So now I have my equation, y equals 106 e to the negative 0.054, because we like 3 decimal places, t plus 74. Okay, I think that was a fairly long video. I apologize, but there's some really good examples, some really good of when am I ever going to use this type of stuff. Thank you for watching.